Hello, welcome to another module in this massive open online course. So, we are looking at amplitude shift keying, and we said in amplitude shift keying either we are transmitting the amplitude level A or the amplitude level 0, alright, and the two waveforms are distinguished by the amplitude level. And we have looked at we have looked at the optimal matched filtering at the receiver and the optimal statistic after sampling, that is R of t, we have shown is given as R of t this is either AEP plus n tilde if A naught equals A, or simply n tilde if A naught equals 0. Okay. And we have said in this scenario R t equals AEP plus A tilde. Well, this is a Gaussian. So, we have seen first n tilde in both cases, n tilde is Gaussian, mean equals 0, variance equals n naught by 2 times E p. So, in this case R t is Gaussian with mean AEP, that is the Gaussian shifted to AEP, and variance remains unchanged, that is n naught by 2 times EP. And in this case where you have A naught equals A, in this case it is simply Gaussian with mean equals 0 and variance equals n naught by 2 times EP. So, the probability density functions corresponding to A naught equals A and A naught equals 0 are still Gaussian in nature, and similar to BPSK they are also shifted, but in amplitude shift keying corresponding to A naught equals 0 the mean is still 0, correct, and corresponding to this amplitude corresponding to A naught equals A, the amplitude is A E p. This point is AEP, and by symmetry midpoint is AEP divided by 2. Therefore, one can decide A naught equals, well, A if R t is greater than or equal to AEP by 2, and on the other hand decide A naught equals 0 if R t is less than AEP by 2. Now, one other way to look at this is we have, remember, R t equals AEP plus n tilde, and here we have this is corresponding to A naught equals A and this is corresponding to A naught equals 0. Now, if we consider R tilde t equals R t minus AEP by 2. Now, if you subtract AEP by 2, then we have, well, R tilde t will be AEP minus AEP by 2, that is AEP by 2 plus n tilde if A naught equals A, and this will become minus AEP by 2 plus n tilde if A naught equals 0. Now, you can see there is symmetry, it is symmetric about 0. So, now you can see this is similar to BPSK, similar to BPSK with AEP replaced by AEP by, this is similar to BPSK with AEP replaced by AEP by 2. Therefore, again now we have something that is similar to BPSK, that is AEP by 2 plus n tilde minus AEP by 2 plus n tilde. Remember, for BPSK binary phase shift keying, we had AEP plus n tilde minus AEP plus n tilde. Therefore, in that sense this is similar to binary phase shift keying with AEP replaced by AEP divided by 2. Hence, the optimal detector again can be to decide A naught equals A if R tilde t greater than or equal to, well, 0 implies R t minus AEP by 2 greater than equal to 0 implies R t greater than or equal to AEP by 2. So, decide. So, the decision rule is decide, again we get back the same decision rule, R t, which is R t greater than or equal to AEP by 2 implies decide A naught equals A, R t less than AEP by 2 implies decide A naught is equal to minus A. Okay. So, this is the decision rule that we have. Now, if you look at the probability of bit error, again the probability of bit error can now be derived easily. Now, you see this is similar to BPSK. If you look at R tilde t, this is equal to, well, AEP by 2 plus n tilde AEP by 2 minus AEP by 2 plus tilde. So, bit error rate is similar to that of BPSK with AEP replaced by a bit error rate or probability of bit error, it is the same thing, both mean one and the same. Is similar to BPSK with AEP replaced by AEP by 2. Therefore, probability of error is Q AEP divided by 2 AEP divided by 2 divided by square root of n naught by 2 times EP. Now, we are going to substitute, which is equal to, well, let me first simplify this, which is equal to Q square root of A square EP by n naught, which is equal to 2 A square EP by 2 n naught. Okay. Now, substitute EP equal to 1, that is pulse normalized to unit energy, and remember we have calculated in amplitude shift keying, we have said that for average bit energy EB, A square must be equal to 2 EB. So, substituting A square equals 2 EB, we get P equals Q square root of A square is 2 EB into EP is 1 divided by 2 n naught divided by 2 n naught, which is equal to q square root of EB over N naught. That is your probability of error. Okay. So, this is the probability of error for amplitude shift key. This is the probability of error for amplitude shift key. Now, compare this with probability of error of binary phase shift key, compare it with probability of error of binary phase shift keying, which is equal to q, remember this is q square root of two EB over N naught. This is the probability of error of binary phase shift key. So, for amplitude shift keying, it is equal to q square root EB over N naught. For binary phase shift keying, probability of error for binary phase shift keying is q square root 2 EB divided by N. Look at this, the argument of binary phase shift keying is higher, that is, this is square root of 2 EB over N naught. The argument, that is argument of the q function for amplitude shift keying, is simply square root of EB over N naught, and the q function is a, remember, it is important to realize that the q function is a decreasing function of its argument, because q function represents the tail probability of the Gaussian probability density function, correct, of the Gaussian random variable. Therefore, as the argument is increasing, the tail probability is decreasing, therefore, the q function is decreasing, alright. So, remember QU, if you look at QU, what is QU? If this is the standard Gaussian random variable, that is mean equal to 0, variance equal to 1, this is the standard Gaussian random variable. Q of u is simply the probability that the standard Gaussian random variable Q of u is simply this probability, this is your Q of u equals probability that the standard Gaussian RV is greater than or equal to u, which we have written as integral u to infinity 1 over square root of 2 pi, correct, e to the power of minus t square by 2 dt, and therefore, you can clearly see this is a decreasing function of u. As u is increasing, this is a decrease, this is decreasing, this is a decreasing function of u. As u is increasing, the q function is decreasing. Therefore, this means that q, the important point here is that q square root of 2 EB over N naught is less than q of square root of, well, EB over N naught, which means, which implies that probability of error for BPSK for the same bit energy is less than or equal to probability of bit error for amplitude shift key. This is an important result, and this comparison, remember, it is a fair comparison because we are comparing it for the same bit energy. Remember, the important consideration here is that both modulation schemes have same bit energy equals EB, both the modulation. Therefore, this is a fair comparison, that is the important point. The comparison has to be same, because if one of them has a higher energy, right, if one of them has a higher energy, so if one of them, this is basically a fair comparison. Okay, because if one of them has a higher bit energy, naturally the bit error rate is going to be lower. So what we are doing is we are maintaining a constant average bit energy across the schemes and comparing the bit error rate performance. And what we have seen is that the bit error for the same average bit energy EB, the bit error rate or the probability of bit error of binary phase shift keying is lower in comparison to that of amplitude shift keying, and this is an important observation. Okay. And how much improvement in bit error rate does binary phase shifts? Now, one can ask the question, how much improvement or bit error rate or BER how much improvement in bit error rate but does BPSK provide? Now, if you look at this, for the same bit error rate, if you look at this, for the same bit error rate in BPSK, we need half the average bit energy. That is, if you use half the average bit energy, bit error rate for BPSK, that is bit error rate for BPSK is 2 half EB divided by N naught equals Q square root of, well, EB over N naught. Okay. So, this is bit error rate. So, this is the bit error rate of BPSK for half bit energy. That is for that is the bit error rate of BPSK with half the average bit energy is same as that same as the bit error rate of amplitude shift keying with bit energy EB. Okay. So, to provide a similar bit error rate performance, provide a bit error rate performance similar to that of amplitude shift keying, binary phase shift keying requires only half the bit energy as half the average energy per bit as that of amplitude shift keying. Okay. So, if you look at this, for same bit error rate, for an identical bit error rate, for the same bit error rate, BPSK half the average bit energy as that of amplitude shift keying, which implies that energy per bit of BPSK equals half energy per bit of amplitude shift keying. Now, if we convert this into dB terms, this implies that 10 log 10 energy per bit of BPSK equals, well, minus equals, well, 10 log 10 half plus 10 log to the base 10 energy per bit ASK, which implies that the dB difference between the average bit energy of BPSK and ASK is 10 log to the base 10, that is the dB difference, minus 10 log to the base 10 energy per bit ASK equals minus 10 equals minus 10 log to the base 10 2. 10 log to the base 10 of 2 is 3, this quantity is approximately 3, which means this is minus 3 dB. So, which means that if you look at the dB difference between the average bit energy, correct, if you look at the dB difference, if you look at energy per bit BPSK in dB terms, let me make that clear, this is in terms of dB minus energy per bit of amplitude shift keying in dB, this is equal to minus 3 dB. Or what this means is, for the same bit rate performance, binary shift phase shift keying requires 3 dB less average bit energy in comparison to amplitude shift keying, or in other words, amplitude shift keying requires 3 dB higher average bit energy in comparison to binary phase shift keying. Therefore, binary shift phase shift keying is much more efficient, correct, is more efficient than amplitude shift keying. Okay. So, in dB terms, for same BER BPSK, lower average energy per bit, or in other words, or basically ASK, amplitude shift key, three dB higher EB when compared to or basically amplitude shift keying requires 3 dB higher EB when compared to BPSK for the same bit error rate. So, that is the interesting observation that we would like to make. So, what we have seen in this module is we have completed our discussion of amplitude shift keying. We have described amplitude shift keying, which is a different model for a digital communication system, a different modulation scheme for a digital communication system, in which the different waveforms are distinguished by their amplitude levels. Correct. We have seen what is the optimal filter, optimal match filter receiver, what is optimal received signals or received signal test statistics after match filtering and sampling, and also we have seen what is the optimal decision rule followed by the probability of error, and what is the efficiency of amplitude shift keying in comparison to binary phase shift keying. All right. So, we will stop here and continue with other aspects in the subsequent modules.